Strokes-Einstein and Gibb's adsorption equations for the determination of hydrodynamic or solvated ion radii. First is Stokes-Einstein equation, which is actually a diffusion coefficient that is expressed in terms of the kinetic energy and frictional force, showing diffusion of spherical particles through a liquid with dominated laminar flow. So here the equation in red color is known as Stokes-Einstein equation, which is the expression of diffusion coefficient is equal to Kb, where Kb is the Boltzmann constant and T is the temperature, and 6 pi eta A is actually the frictional force, in which A is showing the hydrodynamic radii or the solvated ions radii. This equation is equivalent to the electric mobility equation, that is mu kbt over q, where mu is the electrical mobility of the charged particles, where q is the electrical charge of a particle. So in this equation and discussion, we are concerned about the hydrodynamic or the radii of solvated ions, that is represented as A. So let's discuss with examples. So let's take the example of lithium ion, and if we move to down the group, the size of the ions is increasing, in this group the density of the lithium ion is highest as the charge volume ratio is lowest, showing its ionic density. And due to the higher charge density of the smaller ions, so its higher charge density value, the lithium ion have more number of solvated solvent molecules. So the higher the charge density, higher will be the number of solvated molecules, because the effect of this charge will extend to higher number of molecules around the charge. So if we consider the physical picture of the lithium ion, it should move faster when placed in an electric field, where E is the electric field strength and del phi is the electrical potential difference. So according to the smaller size of this lithium ion, it should move very fast, but in reality it have lower mobility, and among the group its mobility is lowest. That's observed to be due to the higher number of solvated molecules associated with this smaller ion, making the hydrodynamic or solvated molecules radius higher than observed to be for lithium ion solely. So here the highly solvated lithium ion will have least mobility, and thus lower electrical conductivity. So if we move from the lithium to cesium ion, the electrical conductivity increases. Why? Because the restricted movement of the lithium ion, that is due to the heavily solvated molecules of the solvent around this lithium ion due to its higher charge density. Here one thing is needed to be remember that the lithium ion, when isolated, it must have highest mobility and thus electrical conductivity. But in the case of solvated lithium ion, the effect is inverse. Here we have observed that the smaller ionic radius will attract more number of solvated ions. So here we can say that the smaller ionic radii, higher number of solvated molecules. So practically this is the reason that lithium have least mobility in its group, and we have discussed that the smaller radii will have higher number of solvated molecules. So let's take another example, that is the copper sulfate pentahydrate. In this example, the size of copper is smaller than the sulfate ion. So the total number of solvated or hydrated water molecules is 4 for the copper and 1 for the sulfate ion, which is showing that the smaller size of ion will lead to the smaller radius, where the more attraction with the solvent, that will result in the formation of higher solvated radius or high hydrodynamic radius, leading to lower mobility and thus lower conductivity. So according to this concept, hydrogen ion have smaller size and it should have less conductivity due to this concept, but it have more electrical conductivity. That is because when hydrogen ion is in water, have different ionic species like hydronium ion, and when 3 water molecules are attached with hydrogen, to get this kind of charge, when 4 water molecules are attached with hydrogen ion, then H9O4 positive structure is formed. So simply we can say that the hydrogen is shifted from one water molecule to other water molecule. So this phenomena is known as proton jumping, through which a proton is shifted from one water molecule to other water molecule. That's why the mobility of this hydrogen ion is highest. But the overall discussion discussed before for other ions are applicable accordingly. Now come back to the Strokes-Einstein equation, in which A is the radius of ion that is solvated, and it also includes aggregated solvent molecules. So this A is actually the aggregate radius. If the solvent molecules are water molecules, then it will called as hydrodynamic radius. This radius can be calculated from the solid form as, at first, the density of solid solute will be calculated from the physical methods. Using molecular formula, we can calculate the molar mass. From molar mass and density, we can calculate the molar volume, and from molar volume divided by the Avogadro's number, we can calculate the volume of one atom, and in this way we can calculate the theoretical radius of one atom using this relation. Now let's see how we can calculate the radius of solute particles using Gibb's adsorption equation. This equation gives the value of hydrodynamic radius for the solute, that is hydrophobic. So if the solute is hydrophobic, it will move towards the surface, and the concentration of solute at surface is known as surface excess concentration, and the mobility of ion at surface is known as ionic mobility. At surface, having unit of mole per meter square. So this symbol represents the surface excess concentration, which is related to more ionic mobility at the surface. The unit of surface excess concentration is mole per meter square. So let's a surfactant that is the schizophrenic molecule, when added to water, so this hydrophobic chain will tend to direct at the surface, and when large number of surfactant molecules are added to the water, at a time will reach when the surface will be concentrated with these hydrophobic molecules. When the surface of the solvent is replaced with the hydrophobic molecules, then the surface properties of the pure solvent and the saturated surface will be changed. So when the surface is saturated, there will be an equilibrium between the bulk and surface species, then they will exchange the position, that is the bulk or either the surface. So at this saturated or the surface excess concentration, the equilibrium is established, which is represented as change in surface tension, that is change from the pure solvent surface to the saturated surface excess concentration, equal to sum of the surface species into change in chemical potential. So d mu is change in chemical potential. So the change in individual chemical potential is represented as minus RT d log natural of activities. So we have activity for solute, that is 1, and the second species is solvent. For solvent I is 2. So by adding the value of change in chemical potential to the change in surface tension dr, that is gamma, minus RT summation of surface excess concentration d log natural of activities AI. So let's rewrite this equation for solute and the solvent. So the change in the surface tension is equal to minus RT surface excess concentration, that is for solute, log natural activity, that is for 1. Same term for the solvent. Let's call it equation number 1. Now assume that the activity is equal to concentration. Why? Because we can assume that the solute interaction are 0, and for these kind of interaction the activity coefficient is 0, that is controlling the value of activity, that is the product of activity coefficient and concentration. So when the solute interaction are equal to 0, the activity coefficient should be equal to maximum, that is controlling the solute interaction. So this is true for very dilute solutions. So according to this assumption, we are equalizing the activity is equal to concentration when the activity coefficient is considered to be equal to maximum, that is the absence of solute interaction, which are also known as ion pairing. So in this way we can rewrite this equation number 1 as equation number 2. Here the activity coefficients F1 and F2 are considered to be equal to 1, and as well as the differential of the activity coefficient, that is a constant value, must be equal to 0. So we can rewrite this equation as, whereas for the case of the F1, we can rewrite as the differential of activity coefficient is 0 when it's not equal to 1. So overall we can rewrite this equation as according to our assumption, when F2 is equal to 1. But in some cases, when the ionic interactions are present, the equation minus RT square root of 2 log natural F2 C2 will be used. So here we can rewrite this equation number 3 in terms of log as equation number 4. For experimental determination, the concentration of the solution will be changed through variation in increasing pattern, and respective surface tensions will be calculated using the experimental method that should have shown the decrease in value. Then log natural of concentration will be calculated for respective concentrations. Using this data, the plot between the surface tension and the log natural of concentration should give this kind of pattern, and the slope must give the value of minus RT, the surface excess concentration. Using this surface excess concentration, the area of the surfactant can be calculated using relation, that is the 1 over Na, that is Avogadro's number, and the surface excess concentration. The unit of surface excess concentration is mole per meter square, whereas the unit of Avogadro's number is per mole. So overall the unit of this equation is meter square. So we can rewrite this equation as 10 to the power 20 Here we can get the area in angstrom square. So by introducing the value of Avogadro's number, again we can rewrite this equation as 1.67 into 10 to the power minus 4 over the surface excess concentration having unit mole per meter square. So simply we can get this simplified formula to calculate the area of the surfactant in angstrom square. So if the unit of the surface excess concentration is taken in mole per meter square, this formula will be used, and when it's taken in mole per centimeter square, then this formula will be used. So usually we get two kind of surface areas of the surfactants. For example, if the area is 2.2 angstrom square or round about it, then the surfactant is present in vertical form, just like in this way. And when the area is round about 23.2 angstrom square, then this position is laid down position of surfactant over the surface of solvent, and the area between these two values will have bent position like this. So in this way we can calculate the radius of the solute using experimental method, in which surface area will be calculated using surface tension technique. So here the area can give the value of hydrodynamic radius from this calculation. So similarly, the radius can be calculated from the theoretical calculations as discussed above. So here this radius will be calculated from volume calculations. So the radius calculated from the volume or theoretical calculations should include only the radius of solute, whereas the radius calculated from the experimental method that is giving the hydrodynamic area or the surface area will give the value of hydrodynamic radius. So hydrodynamics radius must be higher than the radius of solute.